तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the 5th lecture of Module 4 of Design of Members. In this lecture, we shall study the design of sections for flexure by a special method called the Magnel's graphical method. The determination of maximum and minimum eccentricities at the critical section helps in placing the CGS in the beam. But with different types of possible sections, the computations increase. The graphical method proposed by G. Magnel gives a visual interpretation of the equations involved. What we have studied till now is the computation of the maximum and minimum eccentricities at the critical section of a beam. From there, we can place our tendon and the CGS. We also learned about the limiting zone of placing the CGS throughout the span of the beam. But if we are trying with several types of sections, then the computations increase, and at that time it is better that we can adopt some faster method of computation. The Magnel's graphical method is one such type which can be implemented in a computer program, and the sections can be verified of their possible application, and the combination of the prestressing force and the eccentricity can be selected quickly. Once this method is implemented in a computer program, the graphical method is faster than the hand computations. There are essentially 4 stress conditions to be checked at the critical section. These conditions are as follows. At transfer, we need to make sure that the stress at the top of the section is less than the allowable tensile stress in the concrete, and the stress in the bottom should be greater than the allowable compressive stress for the concrete. Now, when we are writing these equations, these are algebraic equations. A stress, if it is compressive, is considered to be negative, and hence this equation Fb greater than FCC allowable means the negative value of Fb is numerically smaller than the numerical value of FCC allowable. At surface, the stress at the top should be less than the allowable compressive stress at surface. Now, if we write that in an algebraic equation, since both the quantities Ft and FCC allowable are negative for their compressive stresses, in that case, since the numerical value of Ft has to be small, the algebraic value of Ft will be greater than FCC allowable. And the other stress condition at surface is that the stress at the bottom, which is tensile, should be less than the allowable tensile stress at surface. Here, Ft is the stress at the top of the section, and Fp is the stress at the bottom of the section. To repeat, the above expressions are algebraic inequalities where the stresses Ft and Fp are positive if tensile and negative if compressive. The allowable tensile stress FCT allowable is assigned a positive value, and the allowable compressive stress FCC allowable is assigned a negative value. Thus, if we plot the stress value in an axis, the FCT allowable is the allowable tensile stress, and it is assigned a positive value which falls on the right side of the 0 value, and FCC allowable is the allowable compressive stress which is a negative value, and it falls on the left side of the origin 0. Now, since these are the two limits of the stress conditions, if any tensile stress has to be less than FCT allowable, then we can write the equation that the stress is less than FCT allowable, which falls in the positive side of the axis. Whereas, when a negative stress, its numerical value has to be less than the numerical value of FCC allowable, then if we write the algebraic equation along that axis, we have to write that the stress is greater than FCC allowable, since as we move from left to right, the values increase in an algebraic sense. The allowable stresses were explained in the module of Introduction, Prestressing Systems and Material Properties. Here we are not going into that again, but let us just remember that we do have allowable stresses at transfer and at service. These values are different because the concrete has different strength at transfer and at service. It is to be noted that the values of FCC allowable at transfer and at service are different. They are calculated based on the strength of concrete at transfer and at service respectively. Similarly, the values of FCT allowable at transfer and at service can be different. As per IS 1343-1980, the values of FCT allowable at transfer and at service are of course same. Thus, for IS 1343, the allowable tensile stress at transfer and at service have been made same by the reasoning that anyhow the values of the tensile stress should be small, and hence a same value has been assigned as the allowable tensile stress both at transfer and at service. The expressions of the stress at the top and at the bottom in the four inequalities are expressed in terms of the initial prestressing force P0, the eccentricity E at the critical section of the member, and the section properties A, then the section moduli ZT, ZB, the Kern levels KT, KB, and the self-weight moment MSW. After transposition, 1 by P0, that is the inverse of the prestressing force at transfer, is expressed in terms of the eccentricity E by linear inequality relationships. That means the idea is that the four inequality relationships that we have seen for the stress conditions, we can express the stresses in terms of the prestressing variables and the section properties and the external load. Now, we transpose the terms such that we express the inverse of the prestressing force at transfer, which is 1 by P0, in terms of the eccentricity E. These four inequality relationships are then plotted in the 1 by P versus E plane to get the graphical representation of the four inequality relationships. For a selected section, these relationships are plotted in the 1 by P0 versus E plane. The acceptable zone shows the possible combinations of 1 by P0 and E that satisfy all the 4 inequality relationships. For the selected section, a combination of P0 and E can be readily calculated from the acceptable zone. Let us now understand this method in a step-by-step fashion and try to have the concept clear by the visual interpretation of the inequality relationships. The method is explained in a general form. For type 1, type 2 and type 3 members, the value of allowable tensile stress is properly substituted. For type 1 member, the allowable tensile stress is 0. For type 2 member, the allowable tensile stress is such that it is less than the cracking stress. For type 3 member, the allowable tensile stress can be greater than the cracking stress, but the crack width should be limited, and hence there is an upper limit of the allowable tensile stress. First, let us see the equations at transfer. At transfer, the forces acting in the section, which we are now just considering to be concrete, are the pre-stressing force P0 and the self-weight moment MSW. The stress diagram across the depth of the section has a value of Ft at the top, which can be tensile, and a value of Fb at the bottom, which is compressive. The distances of the top and the bottom from the CGC are denoted as Ct and Cb respectively. The stress at the top is calculated from P0 E MSW as follows. We are going back to the stress concept of determining the stress. That means the stress at the top consists of 3 components. First is the uniform component, which is minus P0 by A. The second is the component due to the eccentricity of the pre-stressing force, which is positive due to the tensile at the top, which is P0 times E times Ct divided by I, and then the third term, which is due to the self-weight, and it is negative since it is compressive due to the self-weight, and that is equal to minus MSW times Ct divided by I. First, we are grouping the terms with P0 together, and also with the term with the self-weight moment, we are substituting the section modulus Zt, which is equal to I divided by Ct. And then we can write Ct divided by R square is equal to 1 by Kb. This is from the definition of the current zone. Now, this is the expression of the stress at the top at transfer, and the inequality relationship is Ft should be less than or equal to Fct allowable. Once we substitute the expression of Ft in this inequality relationship, we get a relationship which relates P0 with E. To get that relationship, we are transposing the terms such that on the left hand side of the inequality, we are retaining 1 by P0, and on the right hand side, we are retaining the eccentricity E, the geometric variables Kb, Zt and A, the self-weight moment MSW, and the allowable tensile stress Fct allowable. All these values have come to the right hand side, and now we have an equation from the first stress condition which relates 1 by P0 with the eccentricity E. This is an inequality relationship. That means to satisfy the stress condition, 1 by P0 has to be greater than or equal to the value which is calculated from the right hand side. The straight line given by the above inequality is plotted in the 1 by P0 versus E plane, and the acceptable zone is shaded. The equation that we had seen earlier, we are plotting in the 1 by P0 and the E plane. If we look back into the equation, we see that if E is equal to KB in this on the right hand side, then the right hand side becomes 0. Hence, we can understand that this equation or the straight line passes through the point KB. At that instant, 1 by P0 is equal to 0. Now, since in the inequality relationship we have 1 by P0 has to be greater than the value on the right hand side, the acceptable zone in this plane is the zone above the line, and that has been shaded, and any combination of 1 by P0 and E which falls above the line will satisfy the stress condition that Ft is less than or equal to Fct allowable at transfer. The second stress condition at transfer is Fb has to be greater than Fcc allowable in an algebraic sense, because both these values are actually negative values. We are calculating the stress Fb just as before. It consists of the uniform component, which is minus P0 by A. Then it has the varying component, which is due to the eccentricity of the prestressing force, which is minus P0 times E times Cb divided by I, and since this is compressive, we are placing a negative value, plus the component due to the self weight, which is MSW times Cb divided by I, and the component due to self weight is tensile, and hence we are placing a positive value. Again, we are grouping the terms of P0 together, and for the term with MSW, we are substituting the section modulus Zb is equal to I divided by Cb, and once we write this expression after these substitutions, we get an expression of the stress at the bottom in terms of P0 and E and the section variables and the self-weight moment. We have to satisfy the inequality relationship that Fp is greater than or equal to Fcc allowable. Again, this equation is an algebraic sense, and once we substitute the expression of Fb and we transpose the terms in such a way that on the left hand side we have 1 by P0, and on the right hand side we have all other variables, which includes the eccentricity, the section properties and the self-weight moment, we get the second inequality relationship from the stress condition. And here also we see that if E is equal to minus kT, that means if the eccentricity is such that the CGS is located above CGC at the top count point, then 1 by P0 will be equal to 0. And hence, when we plot the corresponding straight line, this straight line passes through the point where the E has a negative value of minus kT, and any value above the straight line is an acceptable value. Since in the equation 1 by P0 has to be greater than the value which is computed on the right hand side, any value above the straight line is acceptable. This is the second stress condition. and thus we find that now we have got two stress conditions at transfer interpreted in the 1 by P0 versus E plane as two straight lines, and for each straight line we have an acceptable zone for the combination of P0 and E. Next, let us move on to the computations at service. At service, we have to satisfy that the stress at the top has to be greater than or equal to FCC allowable. Both these values are compressive and hence negative, and this equation is in an algebraic sense. At service, the prestressing force is denoted as eta times P0, where eta is a fraction of the initial prestressing force which has reduced due to the long term losses, and mt is the total moment due to the dead load and live load. Thus, the effective prestress Pe is expressed as eta P0, where eta is the ratio of the effective prestress and the prestress at transfer. We see that we have a compressive stress at the top and tensile stress at the bottom. First, we are writing the expression of the compressive stress at the top. The first term is a uniform component, which is minus eta P0 divided by A. The second is the tensile component due to the eccentricity of the prestressing force, which is eta P0 times E times Ct divided by I. And the third component is a compressive component due to the total moment, which is mt times Ct divided by I. We are grouping the terms with P0 together, and for the term with mt, we are substituting the section modulus Zt is equal to I divided by Ct. And once we have done the substitution of the Kern level Kb is equal to R square by Ct, we get an expression of the stress at the top Ft in terms of the prestressing variables and the section properties and the total moment. To satisfy the inequality relationship Ft greater than Fct allowable, Cc allowable, we are substituting the expression of Ft, and then we are transposing the terms such that we have 1 by P0 on the left and all other variables on the right side, and we arrive at an equation which is the third inequality relationship related with the stress condition at service. And here we find that if E is equal to Kb, then the numerator on the right hand side becomes 0, and hence 1 by P0 will be equal to 0. Thus, we can understand that when we plot the straight line, it will pass through the point E equal to Kb, and note that in this inequality relationship 1 by P0 has to be less than or equal to the value on the right hand side. Unlike the equations at transfer, where we had 1 by P0 has to be greater than the value on the right hand side, here we are having 1 by P0 has to be less than or equal to the value on the right hand side. When we plot the equation passes through the point E equal to Kb, and the zone below the straight line is the acceptable region, because 1 by P0 has to be less than the value which is computed on the right hand side. The fourth stress condition, which is the bottom stress at service should be less than the allowable tensile stress at service. We are seeing the forces that are acting, which are eta P0, the effective prestress, and the total moment, and we are calculating the bottom stress, which is equal to the uniform component eta P0 divided by A, which is negative, then minus eta P0 times E times Cb divided by I. this is also negative because the eccentric pre-stressing force causes compression at the bottom, and then we have the tensile stress due to the external moment, which is mt divided times Cb divided by I. And we are grouping the terms with P0. For the term with mt, we are substituting Zb is equal to I divided by Cb, and once we have substituted, we get an expression of the stress at the bottom in terms of P0, E, the section properties, and the total moment mt. To satisfy the inequality relationship Fb less than or equal to Fct allowable, we are substituting the expression of Fb, and again we are transposing the terms such that we have 1 by P0 on the left hand side and all other terms on the right hand side. For this equation, we see that if E is equal to minus kT, then the numerator will be 0, and hence 1 by P0 will be 0 in the equality relationship, and hence the straight line will pass through a point E equal to minus kT, and the inequality relationship shows that 1 by P0 has to be less than or equal to the value given on the right hand side. When we plot this inequality relationship, the straight line passes through the point E equal to minus kT, and the values of 1 by P0 has to be less than that in the straight line, less than or equal to, and hence the region below the straight line is the acceptable region for the combination of 1 by P0 and E. Thus, we have the fourth inequality relationship and the corresponding straight line in the 1 by P0 versus E plane. Now, at this stage, we are having 4 straight lines for the 4 stress conditions, and now we are superposing those straight lines in the 1 by P0 versus E plane to determine the common acceptable zone which satisfies all the 4 stress conditions. The 4 lines are plotted together. The common region is the acceptable zone. What we have found that the 2 equations for the stress conditions at transfer, which are 4E1 and 4E2, for these 2 equations, any point lying above the straight lines is acceptable. Whereas, for the stress conditions at surface, which are represented by the lines 4E3 and 4E4, any combination which lies below the straight lines is acceptable. The common region which is acceptable for all the 4 stress conditions is the area which lies in between these 4 straight lines, and that region is called the acceptable zone. Thus, for a particular section, we may have an acceptable zone, and we have the freedom of selecting values of P0 and E within that acceptable zone. If there is no acceptable zone for a section, then it implies that that section is not suitable for the given loading conditions, and if the acceptable zone for a section is small, then it implies that we do not have much freedom in the combinations of P0 and E, and we have to select a value which lies in that acceptable zone. Thus, this graphical method gives a visual interpretation of the stress conditions that we have to satisfy, and it helps us to select the combination of the effective pre-stress at transfer, which is P0, and the eccentricity E from the acceptable zone. A combination for a trial section, the pre-stressing force P0 and eccentricity E at the critical section can be plotted in the form of the above graph. If the point lies within the acceptable zone, then the combination is valid and it will satisfy all the 4 stress conditions at transfer and at service. Let us understand the Magnel's graphical method by an example problem. The section shown in the next slide is designed as a type 1 member with the total moment is equal to 435 kilonewton meters, which includes an estimated self weight of MSW equal to 55 kilonewton meters. The height of the beam is restricted to 920 millimeters. The pre-stress at transfer FP0 is equal to 1035 Newton per millimeter square, and the pre-stress at service FPE is equal to 860 Newton per millimeter square. Based on the grade of concrete, the allowable compressive stresses are 12.5 Newton per millimeter square at transfer and 11 Newton per millimeter square at service. The properties of the pre-stressing strands are given below. Type of pre-stressing strand is 7-wire strand. The nominal diameter of each strand is 12.8 millimeters and the nominal area is 99.3 millimeters square. For the section, find the acceptable zone by Magnel's graphical method. Compare the design values of the eccentricity E and the inverse of pre-stressing force at transfer, which is 1 by P0, with the acceptable zone. This problem we had solved earlier, and from the preliminary design we had calculated the type of the section, and then from the final design we had selected the final dimensions. The flange width was 435 millimeters. It is a section symmetric about the horizontal axis. We have satisfied the requirement of the height, which is 920 millimeters. The thickness of the width, the web and the flange both are 100 millimeters. The calculated eccentricity has been rounded off to a value of 290. That means the CGS is located at 290 millimeters below CGC, and we had selected 10 7-wire strands with P0 equal to 994 kilonewtons. This design was for a type 1 section satisfying the stress conditions which were calculated from basic principle. Next, we are checking this section based on the Magnel's method, but before that we need to calculate the geometric properties of the section to plot the 4 lines in the 1 by P0 versus E plane. That means our first step is the calculation of the geometric properties of this section, from which we will be able to draw the 4 lines. The section is symmetric about the horizontal axis, hence the CGC lies at mid depth. The section is divided into 3 rectangles for the computation of the geometric properties. From the CGC, the centroid of the top rectangle is at a distance 410 millimeters. The distance of the top fiber and the distance of the bottom fiber is at a distance of 460 millimeters from the CGC. Remember that this section is symmetric about the horizontal axis passing through the CGC. We are calculating the area of the section. Since A1 is equal to A3, the total area is given as 2 times A1 plus A2. A1 is equal to 435, the flange width, times the depth of the flange, which is 100, and A2 is equal to the remaining part of the depth of the web, which is 920 minus 100 minus 100, which is 720, times the width of the web, which is 100. Once we substitute the values, the area comes 159,000 millimeters square. Next, we are calculating the moment of inertia of the section about the axis through CGC. Here also I is equal to 2 times I1, since I1 is equal to I3, plus I2. To calculate I1, we are using the parallel axis theorem, which states that the moment of inertia about the axis through CGC equal to the moment of inertia through the centroidal axis plus the area of the rectangle times the distance square, where the distance is the distance between the CGC and the centroidal axis of the top rectangle. Now, for this, the moment of inertia about its centroidal axis is equal to 1 by 12 times breadth times depth cube, which is equal to 1 by 12 times 435 times 100 cube. Then to this we are adding the term, the area, which is 435 times 100 times the distance square, the distance is 410. For I2, the centroidal axis is same as the axis through CGC, and hence I2 is equal to 1/12 of the times the breadth, which is 100, times the depth cube, which is 720 to the power 3. Once we have substituted these values, I is equal to 1.78 times 10 to the power 10 millimeter to the power 4. Square of the radius of gyration, r square, is equal to I by a, and when we substitute the values of I and a, we find r square is equal to 112,000 millimeter square. The section moduli ZB equal to ZT equal to I by CT, and once we substitute the values of I and CT, we get the section modulus equal to 38712,174 millimeter to the power 3. The Kern levels KB equal to KT is equal to R square by CT. Once we substitute the values, we get 243.5 millimeters. Thus, at this stage, we have calculated the geometric properties of the section, and next we are calculating the inequality relationships from the stress conditions. First, we are calculating the ratio of effective prestress and prestress at transfer. Eta is equal to PE divided by P0, which is equal to the stress FPE divided by the stress at transfer FP0. These values are given, and 860 by 1035 gives the value of eta is equal to 0.83. Thus, 83% of the prestress at transfer stays as the effective prestress. The first inequality relationship satisfies the condition that at transfer the stress at the top should be less than the allowable tensile stress, which is FCT allowable, and corresponding to the inequality relationship, we are substituting the values of KB, FCT allowable, MSW, ZT. Now, since it is a type 1 section, FCT allowable is equal to 0. That means we are not allowing any tension in this section, and area is equal to 159,000. Once we have substituted these values in this on the right hand side, we find an inequality relationship 1 by P0 should be greater than or equal to 1 divided by 225,897.9, then within bracket minus 1 plus E divided by 243.5. This equation is plotted in the 1 by P0 divided and versus E plane, and this passes through the point E equal to KB, which is 243.5 millimeters, and any point lying above the line is acceptable, and hence that region is shaded as green, and any point lying below the straight line is not acceptable. It will violate the stress condition, and that region is represented as red. Hence, we see that the first stress condition gives a line which demarcates the combination of 1 by P0 and E into two regions. One is the green region, which is acceptable, and the other is the red region, which is not acceptable. The second condition is at transfer, the stress at the bottom should be greater than the compressive stress at transfer, and again this stress condition is in an algebraic sense and both these values are negative. Now for the corresponding inequality relationship, we are substituting the value of Kt, MSW, Zb, A, and the compressive stress at transfer can go up to 12.5, and the negative value makes this positive, and we have the relationship 1 by P0 should be greater than or equal to 1 divided by 2213397.9 within bracket 1 plus E divided by 243.5. When we plot this relationship, this passes through the point E equal to minus Kt, and here Kt is equal to 243.5, and we find that the straight line demarcates the 1 by P0 versus E plane into two regions, and any combination which lies above the straight line is acceptable, and that is shown as green, and any combination lying below the straight line is not acceptable and which is shown as red. Thus here we have drawn the second stress condition in the 1 by P versus E plane, and we have demarcated the acceptable and the unacceptable regions. Next we are moving on to the stress condition at service. The first condition is that the stress at the top should be greater than FCC allowable. Again this is in an algebraic sense because both these values are compressive. The corresponding inequality relationship, we have the geometric variables and the total moment. Once we substitute the variables, the values of Kb, eta, the compressive stress at service which is 11 Newton per millimeter square, values of the total moment which is 435 kilonewton meter, and values of Zt and A, we find the inequality relationship which is 1 by P0 has to be less than or equal to 1 divided by 45358.0 within bracket minus 1 plus E divided by 243.5. This equation, again we are plotting in the 1 by P0 versus E plane. The equation passes through the point E equal to Kb, and any point which lies below the straight line, here it is shown as green, and any point lying above the straight line is unacceptable, and this is shown as red. Thus the third stress condition also gives us a straight line which demarcates the 1 by P0 versus E plane into two regions, one the acceptable region and the other is the unacceptable region. Next we are moving on to the fourth condition, which is the stress in the bottom at service should be less than the allowable tensile stress at service, and in the corresponding equation we are substituting the values of the variables. Kt is 243.5, eta is equal to 0.83, the allowable tensile stress is 0 for a type 1 member. We have substituted the values of Mt, the values of Zb and A, and once we calculate the terms, we find that 1 by P0 has to be less than or equal to 1 divided by 2152587.1 times within bracket 1 plus E divided by 243.5. This is the fourth inequality relationship, and when we plot that in the 1 by P0 versus E plane, the straight line passes through a point E equal to minus Kt, and any point lying below this straight line is acceptable, and hence this region is shown as green. any point lying above the straight line is not acceptable, and that is shown as red. Thus, the fourth stress condition also gives a straight line which demarcates the 1 by P versus E plane into two regions. The four relationships are plotted in the following graph, and the acceptable zone is shown. The zone is zoomed in the next graph, and we know that the calculated values of E and 1 by P0 for the type 1 section are as follows. These are the values that we had designed when we had originally designed this member as a type 1 member. E was rounded off to 290 millimeters, P0 is equal to 994 kilonewtons, hence 1 by P0 is equal to 1 divided by 994 is equal to 0.001 kilonewton to the power minus 1. The solution of the design is shown along with the graph. It lies in the acceptable zone. Once we plot all these four lines, we see that for this particular section, the allowable zone is a small strip on the right hand side, and the solution is shown as a dark rectangle, and indeed it lies within the acceptable zone. Let us zoom into this small part which will show that the solution lies in the acceptable zone. When we zoom into that acceptable zone, we find that the four lines give a region which is shaded as green, and that is the acceptable zone for this particular section under the given load combinations. The selected values of E and P0 indeed lie within the acceptable zone. Hence, the design values are appropriate, and we have selected a substantially large value of E, rounding it off to 290 millimeters, which gives quite a high value of 1 by P0 or a low value of P0, and hence this will make the prestressing more economical. If we shift the design value more towards the right, then we are increasing the eccentricity and reducing P0, but the eccentricity will not be a rounded off value. It depends on the fabrication. If the eccentricity is expected to be a rounded off value, then 290 millimeters is okay, but if there are methods for having precise location of the CGS, then we may increase E beyond 290 within the acceptable zone, and that value will not then be a rounded off number, but it may give a slightly lower value of the prestressing force P0. Thus, this graph explains the application of the Magnel's graphical method for the type of section which has been selected for this particular problem, and the prestressing variables P0 and E that have been designed for this type 1 member. In fact, it lies in the acceptable zone, and hence these values can be used since they satisfy the stress conditions. Thus, in today's lecture, we studied the design of sections for flexure by a special method which is the Magnel's graphical method. In our earlier lectures, we had learned about the design of type 1 and type 2 members based on the first principles of the stress conditions. But what we see that in a real situation, the computations can be quite involved, especially if you are having different types of section to select from. In that situation, the Magnel's graphical method can be quite handy. It can be implemented in a program, and it can give a visual interpretation of the equations that we are using. Our intention is to have a proper selection of the prestressing at transfer and the eccentricity. If we maximize the eccentricity, then we can reduce the prestressing force. This will be economical for the prestressing operation. Along with this, we have to satisfy the stress conditions. The stress conditions are at transfer, we have to satisfy that the stress at the bottom is lower than the compressive stress at transfer, allowable value. The stress at the top should be lower than the allowable tensile stress at transfer. For service, the stress at the bottom should be less than the allowable tensile stress at service, and the stress at the top should be less than the allowable compressive stress at service. Thus, we have 4 stress conditions which we need to satisfy. For type 1 member, no tensile stress is allowed. For type 2 member, tensile stresses are allowed, but they are less than the cracking stress, hence cracking is not allowed in the type 2 members. For type 3 members, the tensile stress may go beyond the cracking stress, but still there is an upper limit of the tensile stress values, so that the cracking is within a certain limit. Now, this concept of satisfying the stress conditions at transfer and service has been implemented in a graphical form by the Magnel's method. For the first stress condition, which is the Ft, the stress at the top at transfer should be less than the allowable tensile stress at transfer. This gives us an equation which is represented as 1 by P0 greater than or equal to a term on the right hand side which involves the eccentricity. And when we plot that equation in the 1 by P versus E plane, we get a straight line passing through the value E equal to KB, and any point lying above this straight line is acceptable. The second stress condition is that Fb, the stress at the bottom, should be greater than or equal to the compressive stress allowable value. Now, this equation is in an algebraic sense that both Fb and FCC allowable are negative values, and hence in an algebraic sense Fb has to be greater than FCC allowable. And when we write the expression of the stress and transpose the terms, we get the second equation of 1 by P versus E, and when this equation is plotted in the 1 by P versus E plane, we get a line passing through minus KT, and any point lying above this straight line is acceptable, and any point below this straight line is not acceptable. Next, we move on to the service conditions. In the service conditions also, we have 2 stress conditions. The first one is that the stress at the top should be less than the compressive value. In an algebraic sense, Ft should be greater than FCC allowable at service, and when we substitute the expression of Ft, we find an inequality relationship where 1 by P0 should be less than a certain quantity on the right hand side which involves E. When we plot this graph, it passes through E equal to KB, and any point lying below this straight line is acceptable, any point lying above this straight line is unacceptable. Finally, we have the fourth stress condition, which is that the stress at the bottom should be less than the allowable tensile stress at service, and again when we substitute the expressions of the stresses, when we transpose the terms, we find that 1 by P0 has to be less than a certain value on the right hand side, and this straight line passes through E equal to minus kt. Any point lying below the straight line is acceptable, and any point lying above the straight line is unacceptable. When we plot the 4 inequality relationships in the 1 by P versus E plane, we may get an acceptable zone for that particular section under the given loading conditions. If we have a computer program, these graphs can be generated very quickly by inputting the member properties of the section and the loading conditions. If an acceptable zone is there, that means that section is adequate for that loading conditions. If there is no acceptable zone for that particular section, that means we cannot use that section for the given loading conditions. We saw this Magnel's problem by the help of an example which we had solved earlier. Earlier, we had designed this section as a type 1 member, and we had found a certain value of E and P0 based on the equations which were derived from first principles. Today, we solve the same problem by the Magnel's graphical method. First, we calculated the geometric properties, because the Magnel's graphical method involves the geometric properties of the section. We found out the area, the moment of inertia, the Kern levels, the distance of the extreme edges, and the section moduli. Next, we found out the inequality relationships. We had the expressions, we substituted the variables, and we expressed the 4 inequality relationships. Third, we plotted the 4 inequality relationships in the graph 1 by P versus E plane, and once we plotted, we found that there is a small strip which is an acceptable zone, and our previous solution indeed lied within the acceptable zone, and hence it was okay. Thus, today we are ending the design with the Magnel's graphical method, and in our next class we shall move on to the detailing of members for flexure. Thank you.